Good morning. Welcome. Good morning. Good morning, Clara. Thank you for using chatbots. Okay, how is everybody today? Good. Enjoying Calculus 1 so far? I hope. Okay, I see the thumbs up. Thank you. Okay, that's what we will do. Thinking about the section from yesterday, the first one in chapter 2, 2.1, we will, with the idea of the slope of the tangent line, like we will leave this for now, because we will come back in chapter 3, like to introduce the derivatives. But what we have to know, we have to really understand the basic concept of calculus, which is limits. That means from yesterday, we will just take the idea of this limiting process and we will try to investigate. Okay? That's when we know, I hope we remember that the limits, it's kind of like an approximation, like we're getting close enough to the certain point, but not, we can be close enough to the certain point, but we cannot be at that point. Yeah? And we were talking about the instantaneous velocity, instantaneous speed, which basically at a certain point we have no distance, no time, 0 over 0, but we know that it's not exactly 0. We will still create like teeny tiny distance interval, the position and the time interval. Okay, that's we will try to look at these limits. Okay, that's what I have. Let's see. Oh, can I switch? That means the intuitive definition of the limit is, I just type, okay, let's look at the entire slide. That means that's what we can think intuitively. Yes, that limiting position, like we getting close enough, we approximating, estimating. Sometimes it will be like rough calculation, guess. I don't know if guess is the good word, but let's say educated guess, yes, not the wild guess. Okay, that means something like, yeah, we have to think this way. I mean, we can think, you can think your own way, but kind of thinking about these descriptions, these descriptive words. Okay, and we will look today at the limit of the function, limit of a certain model. Like we remember this picture from yesterday, if we would like to find the value of the function, then it's not a problem. We have a point C, x equals to C. I can just find the height. C is in the domain of the function, then we have no problem to allocate that height, which is basically the value of the function at C. But now let's look at this side. Yes, we may say that C actually is not in the domain. Okay, doesn't belongs to the domain. And we may notice we have this open circle, but we still would like to know how function behaves near C. Okay, near means that we are extremely close. Yeah, we remember that. Can you maybe just for the practice, for the warm-up, if we have number, let's say number 3, can you give me the number on the x value on the number line, which is extremely close on the right-hand side? This is the right-hand side, this is the left-hand side. Right-hand side at 3. Okay, that's, we know that we are really close. 3.00001. And then maybe on the left-hand side, this is the right-hand side. This is the left-hand side. Okay, yes, 2.9999999. Okay, that's, we know how. And then when we take the difference, yes, when I will take 3.0001 minus 3, let's say just the difference, or 2.999, that's 0. Oh, actually 1, that's 1. We cannot have 0. Correct, because this will be 9 minus 3. That's we can see it's almost, yes, almost 0. Yes, we will like call arbitrary close, but I will probably call almost 0. Okay, that's we can see almost 0, but theoretically it's not 0. We still have a little bit of an interval. Okay, that's really good. That means now we can see we would like to find out what function is doing near the value c. And the notation is, we will say, we will use the limit notation for this one. Okay, that means this one is the value. That means that we know this is exactly the value. Now, for the limit, we will say limit, remember, and we will check couple of x values on the left-hand side and couple of x values on the right-hand side, and we will get closer and closer to c. We will say x approaches c, but it's not, this doesn't mean that it's equal to c. No, we don't even have the value. I can say the exact value does not exist. Let's put empty. DNE does not exist, right? That means limit of the function, because we always have to have limit of the model of this situation as x approaches c. And now this is the question mark. We have to answer this question today, right? And we may notice, like, if we will go closer, we will get a couple of values, we will get here, because the values near to c, they belongs to the function. We can get them, okay? That's what we can do. Let's take actually the actual function, and then we will investigate. Okay, yes. Let's take our best friend, parabola x squared, okay? And we would like to investigate how this parabola behaves near x equals to 4. Parabola x squared is continuous function, then definitely 4 is in the domain, because that's power, actually, yes, power function, polynomial. Polynomials has domain all of the numbers. That means definitely 4 is in the domain. And if we would like to find the value, it will be just, actually, the function is defined x squared. That means what is exactly the value at 4? Can you help me? What's the, I was gonna write 4 squared, 16. Okay, we know the value. That's not a problem. But now, if we're not looking exactly at 4, right? We just want to check how function behaves near 4. That means if I will take a couple of values like 3.9, 3.999, 3.999, even closer, and then I will check these values. As we can see, and we have the values. Do you see the values in the table? 3.9 squared is this. 3.99 squared is 15.92. Then 15.99, 15.9999. That's what you can say. At 4, what will be the limit? What these numbers are actually approaching. I know that is obvious, I know, but it's a really important concept, okay? I know, you probably think, wow, it's obvious that is 16. Okay, yes, thank you. But let's just get that idea. And then we can repeat the same process on the right-hand side. I can take like 4.1, 4.01, 4.001, 4.001, even closer, and then the corresponding values, it will be then 16.81, 16.08, 16.008, 16.008, and then we may definitely see that these values are also approaching 16. Okay? Okay, that means we can say that the limit of the function f of x as x is getting closer and closer to 4, this limit is 16. We based on all of these numerical values, we prove this. Okay? Okay, that's mean, yeah, it is 16. Really informally, let me remove this. Really informally, we can say this, that this function, we can even see, I put these blue arrows. The function on the left-hand side is approaching that level 16, that height 16. And the same function, yeah, because the curve corresponds to the x values, but we may just look at the curve. The curve is approaching that level 16. As is getting, like as approaches from the left and from the right-hand side. And as we can see, it's approaching level 16. But now what we have to know, we definitely have to know the difference between that 16 and let's say this 16. Okay. The blue one is exactly the value. That means we are exactly on that point. This one, the limit means that function is approaching, but never on that. It's getting closer and closer, like the difference will be almost, yes, we know the difference in these values will be almost 0 if we're getting closer and closer to 4. Okay, but that's what I want my students to know, that this blue 16 is different than the red one. Okay, the value is different than the limit, which arithmetically, like numerically, it's 16 and it's 16. That means it is the same, but the concept is a little bit different. Okay, value, we can say we are exactly at that number. Limit means that we are approaching this number. Yeah? Okay. And yes, I will repeat this. This is supposed to be 4. I see the typo. Okay, that means that's the notation. Yes. Limit as x approaches 4 of the function x squared. We don't know. We found out that is 16. We don't need parentheses, but I can put it. And the value is also 16. Okay? But we know the difference. We definitely know the difference. The red one, the limit is we approaching. The blue one is exactly the value. Actually, I can put exactly the dot. That's exactly that. The red one is the approaching situation. Okay, and then one more time. How we read this, just for the students that you seeing this for the first time. Most of the students seeing this for the first time. The limit of the function f of x equals to x squared is equal to 16 as x approaches 4. That means that's how we will read. Oh, okay. We good with this. And we remember, we still will say equals to. The whole approximation and getting closer, it's like hidden behind the limit. Yeah, the word limit. Okay, and this one, well, let's look at this definition. We will not, yes, it's not exactly formal definition, but it's a little bit, because I'm not using the delta and the epsilon. No, we will not use this unless you are the math major, and then you will take some other classes. Okay, but what we say that the limit of the function f of x as x approaches c is equal to the number L. We can see even if we have empty, yes, if the difference, yes, of the function and that limit, which means that difference, this one and this one, yeah, can be made arbitrarily small by taking the x sufficiently close to the value c, but not equal to. Yeah? And then we can say, yes, L is the limit. L, we can see L is the limit, is the level that the function actually is tending to, approaching, yeah? As x is getting closer and closer to c, sufficiently close. Sufficiently close means almost, yeah, almost c. The difference is almost, yeah, 0. Okay, and then let's just look at, I have one exercise. We will exercise, but I just want, yes, to tell you all of these important theoretical parts. And then we can read in other words. what is important here? Yes, definitely we may find a limit of the function, like I think I mentioned this at the beginning, even if that number doesn't belong to the domain. That's when we can find the limit of the function as x approaches c, but because we're looking at the situation near to c. C could be not like it could be not in the domain. Okay, that's we may not have a value, but we may have a limit. We will have a situation that the limit does not exist, but let's wait. Okay, that means this one. Oh, let's look at this one. That means this exercise is, we will just try to show, because show means proof. That means it's not a typical exercise for our class, but it's nice to know based on the definition. If we have a function g of x equals to 3x plus 1, we have to prove it that the limit of the function g of x as x is approaching 4 is equal to 13. Yeah? You probably see just the substitution. Yes, but let's wait, because we cannot be so like, yes, it's not that obvious. Okay, that's what we can do. Oh, actually, we kind of see the solution at the bottom. 3x plus 1 is just the continuous function, is the line. How this line looks like this, 1 and a negative 1/3. Yeah, the slope is 3. Okay, and let's say this is 4. And we know that the limit is 13. Okay, the limit, that means I will just put the open dot at the moment. That's mean how we can prove based on that definition, this definition. Okay, based on this definition. Let's see. I can say, because this is g of x. That means when I take the function g of x and subtract 13, I'm supposed to get that distance 0, small. Yeah, makes sense? Because the limit means that the value minus the limit is almost 0. Then if I will substitute the formula, but how do we know that this is almost 0? Yes, how do we know? Let's see. I will substitute function 3x plus 1, 3x minus 12. Okay, and then I can factor 3. And now this is the moment. We can see that this expression, yes, the difference of the value of the function minus the limit, we have to prove that is almost 0. We end up having equivalent expression 3 times the factor x minus 4. That's when we can see that this expression is multiplicity of x minus 4, 3 times. And now because we're getting closer to 4, if x, I mean, we can make this arbitrary small. This means arbitrary small, almost 0. If x is sufficiently close to 4, because if x is sufficiently close to 4, then this expression is 0. Then this is the proof that this will be almost 0. I know the mathematical proofs are kind of like sometimes obvious, so obvious, but we have to have them. That's yes, we can make this expression arbitrary small by taking x sufficiently close to 4. That means that's it. That's the proof. Okay? And that's the difference. If we will take some values of the function, let's maybe say this will be g of x. That means that difference, yeah? And maybe on the other side, let's say g of x. That distance, the same on the top, that distance can be almost 0 if this distance is almost 0. Okay, yeah. No, yes, obvious. Okay, that means this is more like, yes, theoretical, but this is, yeah, it's quite powerful. Yeah, because we can see when x is close to 4, this is 0, then this is 0. Then yes, 13 is definitely a limit. Okay, But we will, yeah, we will do more application, more like shortcuts. Okay. Now, exercise or example number 2. Yeah? If you can give me the correct answer for this one, then you understand the general idea. Let me just indicate this is open dot, this is solid, this is open, no solid. Okay, we have A, B, and C. And now for each of these 3 graphs, I would like you to tell me what is the limit as function approaches A and what is the value of the function at A. And this is function f of x, f of x, f of x. Okay, that's what about the first one, A, B, and C. Can you tell me what is the limit? Like, do you see the limit? Now we will just see. I hope we understand the definition. Of course, when we take x sufficiently close to A here, all of these corresponding values are, or maybe I can even just look at the graph. We know the graph is definitely approaching that. This is solid dot. It's approaching that dot is L, oh, at the level L. Yeah, perfect. What about the exact value? What about the exact value? It's also L. It's also L. Perfect. That's mean limit and the value, it's almost the same, but we know the difference. The limit we approaching, function is approaching that height. Value at A is exactly that. Okay, what about this one? What is the limit, yes, how function behaves as x approaches A? Again, we can see almost nothing changed. Function is still approaching that. Now it's the open circle, but doesn't matter. That circle is still at the level L. Perfect. What is the value of the function? No, we do have solid dot, because how we can find the value? We can, that's the A, I can draw the vertical, I can draw a vertical line, and if the line is intersecting at least one, I mean, it has to intersect at one point. That's the definition of the function. If it's intersecting a function, this is the value. That's when I draw a line, I can see this is the intersection. That means, yes, the value is actually M, because we do have that solid dot. Yeah. And now limit. Okay, no, okay, I know, oh, maybe I supposed to put more like, yes, more solid, bigger. Okay, and what about C? What is the limit of the function? As x is getting closer to A, how function behaves? It's still approaching, we can see it's almost the same like example B. It's approaching, we're getting closer to A, but function is approaching that open dot. The open dot is at the level L, yes? And what is the value here? Do we have the value at A? No. D and E, now it's here, because no solid dot. When we draw a vertical line, no intersection. Okay, that's, we can see 3 different functions. But when we look kind of from the distance, the main curve, the main function, it's the same. Okay, you confused by the solid dot. The solid dot means the value, the exact value. Yeah, that's, we may have function like this. I mean, no, it's just the point on the, I could not maybe make them so big. It's basically a graph of the function is the set of points. Yes, like how we can get the graph of the function. We can plot a couple of points and then we connecting them. We know, because it's like infinitely many points. If we would like to, if we will have the formula, that means graph contains infinitely many, yes, any curve. We remember like algebra class in middle school, like we will have a formula and then we will plot, we will get the table, the values, and then we will plot them, we will connect them. That means each dot creates a curve. We may have a formula sometimes that is like piecewise defined function, because this one is good. All of the numbers are in the domain. Yes, all of the in the domain. Yes, except the open dot. That means I can have an entire function and I just, function is missing one value. We call that we have discontinuity, but then it's no value. Yes, no value. And we may have the value put it somewhere else that we can see. And it kind of like this is not here, it's open. Okay, it's drop here. For the C, it's not even, doesn't exist. It's removed completely. We may have, yes, because we may have a function like, we can even have, let me maybe draw somewhere, like if I will draw parabola, I can draw parabola like this. I can remove one point, let's say 2, 4. Yeah, I can have the parabola and one point could be missing. Yeah, that means this is, yes, this is the open dot, like the value is missing. Because my point is, the value is missing, but we still have a function. Still something is going on near to that value. And that's the limit. That's what we would like. That means this one, we can see this, the function doesn't have a value at 2, but it has the limit, which is also 4. If we see this. Okay, I can, yeah, okay, good. That means open dot means no value. There's no value at that level. For the part B, we have the value a little bit lower at the level M. For the part C, no value at all. Yeah? But my point was that we can see, even if we have different situation with the value, still the limit is the same. Because when you look at this function, it's the same shape. Do you see this function? It's the same shape. It's something like this, something like, yeah, the same for all of the 3 examples. Okay, that means limit must be the same. We will just playing with the 1 point. Okay, important slide. Now let's keep moving. I have another graph. Find the behavior or the limit of the function sine over pi over x, sine of pi over x, as x approaches 0. Okay. That's mean this is just the example of course, we don't really know how to investigate. It would be nice if we will see the graph, and I'm providing the graph. Okay, that's the graph. First of all, we may notice x is in the denominator. X is never 0. That means x is not 0. 0 doesn't belong to the domain. And we're looking how function behaves near 0. Okay. Okay, and this is the type of the function that you may see. It's a trigonometric ratio sine, and the behavior, how function behaves is actually oscillating. As x is getting closer, if we will even use the calculator, like closer and closer to 0 on the left-hand side, the value will like oscillate between 1 and the -1, 1, -1. And it's doing this infinity many times, never reach 0. Yes, never. And the same on the right-hand side, 1, -1, 1, -1. That means this is the situation that actually what you will say, what is the limit? How this function behaves? Is this function like approaching? It's not, no, it's never reaching 0. It's always 1 and then -1, 1, -1, 1, -1. That's we cannot really say it's never 0. Because it's always infinitely. I know that is, if we will zoom in, we will like, it will be infinitely many times. That means this function doesn't really go to one direction. Yes, it's not tending like to approach a one finite number, it's oscillating. That means this is the moment and this is the type of the function that we will say that the limit does not exist as a one finite number. Okay, the limit does not exist. And if you will decide to put that answer, we always have to give a little bit of justification, like explanation, then oscillation between 1 and -1 is the explanation. Okay, that means if you will see this oscillation, the limit does not exist because it's oscillating infinitely many times. If I will ask for this type of function, I will definitely provide the graph for you. Yeah, that means don't worry, this is just an example to showing. Okay, let's keep working because we have lots of examples. Yeah, we're learning. Every slide is important, Okay, now another example. Find the limit of the following function as x approaches 0. And now we have piecewise defined function. For positive x's, the value of the function is the formula, or the value is just 1, horizontal constant. And for the negative x's, the value is 0. If x equals to 0, we may see if the value is 1, then we have solid dot. The value belongs here, not here, because we cannot have two values. For one x is 1. Okay, that means now find the limit. We probably learned that finding a limit means finding one point. Find like what function actually does, what function, what value, what height, what level I call sometimes, function is approaching as x is getting closer and closer to 0. Okay, that's we're looking for the value of, for the limit of the function as x is getting closer to 0. That's in what we can say. First of all, do you think this limit exists as a one finite number? No. Okay. That means if you 100% sure that the limit does not exist as a one finite number, then we just say this limit does not exist. And this is true. This is true. Because we cannot say one number, but what we can say, what actually function does on the right-hand side, as x is getting closer and closer to 0 on the right-hand side, function is approaching what level? Function is approaching 1. We can see. Actually, it's a constant. That means it's approaching 1. If x is getting closer and closer to 0 on the left-hand side, what function does? Is approaching 0. That means what we have two different values. Right? And actually we call this because we can this is correct answer. This is definitely correct answer. But again, if we choose D and E, we always have to justify. The previous one was oscillation. This one is two different one-sided limit. Yes? Because we still cannot leave this like not indicating 1 and 0. This is still a good, let's do this. Function is approaching 1, function is approaching 0. Yeah? It's still a good limit. That's mean, but two different behaviors on the left and the right-hand side. And now, left-hand side, right-hand side, and we know the notation almost. We almost know the notation to indicate that we only looking at the limit on the left-hand side, yes, left-hand side, we will put a little negative symbol, like a little minus, like in the place of the power of 0. Yeah? But please remember that negative doesn't always mean that the number is negative. Because that's sometimes the common mistake when I will ask, find the limit on the left-hand side, and then you have options, A, B, C, D, or E. You always pick the negative number. No. Could be anything. This is unfortunately that notation. Left-hand side is indicated as a small negative, but not always. Because for instance, again, typical question that I ask, can you give me the number on the left-hand side at 2? One number on the left-hand side at 2. Perfect, 1.999. It's not negative number, but if we will do something, yes, we will see this notation, it's not negative, just means left-hand side. Okay, that's it. Please remember, because it could save your life. You can pick the correct answer. Okay, and respectively on the right-hand side, we will indicate with the little positive. The same thing. Not always the right-hand side has like a positive answer, positive like outcome. Because when I take number -2, can you give me the number on the right-hand side? What is the example of the number on the right-hand side at -2? -1.99999. Yes, this is -1.99. And can you give me on the left-hand side an example? Because this one we're going backwards, yes? Yes, this one is -2.00001. Okay, that we can see both of them are negative on the left and on the right. Just to tell, because I know how we can have the mistakes. Okay, that means for this one, the entire limit does not exist, but one-sided limits exist, 0 and 1. That we can picture, we know what function does, 0 and 1. We will call that the function is jumping from one value to another at a certain point. Yes? Like when we have not even like levels of river, maybe we have a dam, Hoover Dam. Yeah, okay, just reminds me. Then we have to, it's important to know and every single level on the left and on the right. Okay, that means the limit does not. And now we will have another definition, this one. We can say that the limit of the function exists as x approaches a equals to L if and only if the right-hand side and the left-hand side are identical. Okay? Because if we will have complicated function, we always have to check the left-hand side, the right-hand side, and if function meet, doesn't matter, we may miss that point, but if function meet, then yes, the limit is the same on the left and the right-hand side, and then we can say the entire limit exists. Okay, good. Example number 4. Now really quickly, example number 5, I will just test if we understand. You have to give me all of those answers. We have a function g of x. We see everything, okay? I will not explain. I hope we see the open dot and the solid dot, okay? If you can, yeah. And now, actually, this is typo. I knew it. This is just 5. That's we have to investigate the situation at 2 and at 5, and then 2 and 5. Okay, let's start from the top. Limit. What is the limit of the function g as x approaches 2 from the left-hand side? Yes, from the 2 from the left, we can see function is approaching 3. Perfect. On the right-hand side, because we may draw a line, this is the left, this is the right, function is approaching 1. We can see, like, yes, what function, we know all of these values, the small, the arbitrary small values, sufficiently close, okay? Now, this is one function. We have a jump, we can see, and we have one point is removed, but it's one function. It's a one function. Okay, and what about this limit? The entire limit, yes, we will say does not exist, and this is kind of like a proof. If I will ask you to prove it, you will say one-sided limits are different. Okay. What is happening with the graph, with the function as x approaches 5 from the left-hand side? 5 from the left. Oh, actually, let me do this. Yes, I think it's 2. And what about from the right-hand side? Yes, okay. You got it. And now what we can say, does the limit exist? Like entirely, like as a whole? Yes, the limit exists. And this is also the justification. This is the proof. Now, let's just tell me the value. Does this function has the value, exactly the value at 2? No, because we can see all of the dots, no points, yeah, I'm like making. And what about the value at 5? Yes, when we draw a vertical line, at 1, we will intersect that dot. Yes, okay, good, you understand. Okay, let's keep, that's it. Yeah, that's the concept. I know that you will ace it. That's what I want to say. Oh, okay, I have this a quick exercise. It would be nice, yes, if I will look at your notes, because now I will ask you to draw something. That's what we can do. We also have to be able to do the exercise the other way. I am giving you the conditions, and I just want to see if you can sketch like the graph of the function. Oh, I don't know if I understand. Yes, we have to get the xy plane. This is always the y values. Yes, we know that. I mean the y levels, like the height, the level, the corresponding value. We don't know if we know that the value exists, but always limits I will indicate with the open dots. Did not look like 5 was approaching 2 at all. Oh, let me check which one. Sx is good. You mean Sx is getting closer? Do you think this is not 2? Yeah, always the limit, the final answer is the y values. And this is the situation with x. Okay, no, okay, I know, Santa, I think it's at the level 2. If you will say, do you think it's a little bit lower? 1.9? It could be it's still good, but we just go by 1. Yeah, I think it's, yeah. Okay, that's yes, this is the values. That's what we can do. We have 1. You can also, yes, you can also try. Oh, maybe, I don't know if you can write on the screen. That will be fun. Okay, I know that some students sometimes they try to draw on the screen, but then you have to actually erase because it will stay on all of the slides. Okay, that's mean I will try. Okay, you will help me. What we have? We have 2, and we do. Oh, okay. Somebody is drawing. Yes. Okay. Yes. Yeah. Okay, I can erase. Okay. Yes, actually, yes, that's good. Put where is the solid dot? Where is the open dot? Yes, open dot and the solid dot. I see the solid dot really good because yes, that's it. Really good. Yes, I think that was Nathan. Yes, good. We can see we have but you have to probably, yes, thank you. You look what's happened. You have to, because when I change the slides, it will stay. That's me. Please, yes, thank you. And I will just repeat what you did. You did, oh, that's the value 2, and you draw function like, oh, no. The left-hand side. The right-hand side was this, and that was this. Okay. Or you can have like some parabola, you just draw the lines, it's perfectly fine. But yes, limit on the left is we satisfying that limit, we satisfying this, and the solid dot is here. Yeah, it's really good. Or could be, yes, of course, could be different values, but yeah, that's good. Okay, okay. I think one of the exercise similar to this one is on the written homework. But please, yeah, please be really careful, like showing where is the value and where is not the value. Even if because when you will draw like this, then I will assume that this is solid, yes, it's tiny, but it's solid. Like show that is open, no value at 1. I mean, value is 2, not at that level, -3. Okay, another exercise. Now, another type of limit. Find how the function 1 over x squared behaves as x approaches 0. Basically, find the limit, because x equals to 0 is not in the domain. X is not 0. And of course, we have to find out if this exists. Do we know the graph of the function 1 over x squared? I think we know. Did you watch the very first video on the YouTube list? I am just going through the 9 important graphs. Please check, because when we know the shape of the graph really quickly, it will be so helpful to answer more advanced calculus questions. And this is one of them. Okay, that means that's the hyperbola in quadrant 1 and 2, right? And what do you think? How this function behaves, like just graphically, as we approaching, if the x approaches 0 from the left and the right-hand side. This is one value, another value, another value, another one, and then on the right-hand side, one value, another one, another one. What are the values are doing? They getting greater and greater and greater, bigger and bigger. They actually tends to approach big numbers. And what is the name and the symbol for the big numbers? Of course, infinity. I think I have some numerical values. Yeah, that will be the values. 1, 4, 25, 100, 400, and so on. We can see how, and as x approaches 0. That means x is approaching 0 and values are approaching infinity. Okay, and now, okay, good question. Again, do you see the question? The question is if we have to know the basic graphs, probably I will not provide. The oscillation, the sign, that yes, but the nine basic graphs, no, please check the first video. When you hit the link with the YouTube videos on the front page, on the home page, you know the link. The first video, I think I call section 1.1, but I'm just drawing 9 graphs. And you can draw them somewhere. They are really important. That means this one I will consider as a basic graph. Yeah, I may, but most likely I will not provide. Okay, I hope you like my answer. Okay, that's mean now the notation quickly. I mean, that's almost, lots of information, right? Okay, that's we can say that this limit equals to like infinity, and we can call infinite limit. Yes, infinite limit. Even though infinity is not actually a number, because when we think this function doesn't really approach a finite number, it's getting higher and higher and higher. And we may say, yes, just to describe the situation, we may say it's infinity, it's the infinite limit, and we will definitely say, but also, I have more description. If you will answer, just now, don't get confused. If you will say that this limit does not exist, it's a still correct answer, because does not exist as a finite number. Yes, doesn't exist as a finite number. And now, justification is this. That means when I will ask you this limit on the like a quiz or the midterm or final, I cannot really list like options like this, A, B, C, D, let's say infinity, negative infinity, 0, and maybe D and E. Yeah, because this is correct answer and this is the correct answer. Both of them are correct. Yeah? Because infinity is still like non-existence number, but we will always answer infinity. That means this will be not on the option. Yeah, we would like you to identify these infinite limits. But please remember, it's non-existence. This limit does not exist if somebody asks. Okay, your younger brother, older brother, younger sister, older sister, you can tell the limit does not exist. However, we say infinity. Okay, now another function. Actually, another function, the basic functions, 1 over x. Oh, a little bit shifted. And the graph is not as nice as the previous one. Okay, that means now we have to investigate how function 1 over x behaves at 0. 1 over x is the hyperbola in the first and the third quadrant. Okay, and what we see? We will have the, yes, we will have the one-sided limits, because we definitely see function does something else on one side and some is going to the other direction on the other side. That means, yes, right? If you will see, because you will see based on the graph that function is going different direction, then right away investigate the left and the right and the left-hand side. Yes. The limits of x, we are finding the limit of the entire graph. No. If we are finding the limit of x, but limit as x is approaching a certain number. Yeah, x could be not defined. Yeah, in this situation, we do have actually, yeah, a line that we not touch. Actually, how do we call this line? Do we remember from algebra? It's an asymptote. X equals to 0 is a vertical asymptote. Yeah. That means, yeah, the limit means that we approaching that number, but never we are on that number. Yeah? That means we not exactly at that number. We are near, really close, sufficiently close. Okay, that means what function does on the right-hand side? Everybody can tell me infinity, but what about on the left-hand side? If function goes down, the values are also big, but in the negative direction. And then we can, yes, we have to say this. That's because one-sided limits are different, but even those, yes, even those are non-existence limit. Okay. Oh, okay. Good. Okay, good. Okay, actually, Nathan, did I answer your question? Of the entire graph or the limit of the... Okay, yes. Okay. What about this limit? Yeah, that's also one of the functions that we have to know, natural log of x. We have the graph, natural log of x. I will draw this graph. That means what is the limit of the function natural log of x as x goes to 0. And since the domain is only positive numbers, from 0 to positive infinity, then we only looking on the right-hand side. Yes, function goes down. We can see the blue, negative infinity. That means the limit does not exist, but it's negative infinity. Thank you. Okay, and what else? No, let's leave this one. Let's leave this one later. Okay, that means actually we can finish with the, because I named the vertical asymptote, but we do have a definition of a vertical asymptote. That means the other way, how we can find if the function has a vertical asymptote, especially for the number that is not in the domain. Yes, that's when we're looking at the limit, yes, we have to find the limit as x approaches a, x approaches a. Could be from the left, from the right, could be from both sides. And if these limits are the infinite limits, positive infinity or negative infinity, this means that we have this behavior like we just saw. Function will tend to approach that line. That we can see this is vertical asymptote, even those, yes, because we can see on the left-hand side, the limit is positive infinity. On the right-hand side is a finite number. It's okay, but on the left-hand side, yeah, function satisfies one of those limits. That means function has infinite limit. The same here. On the right-hand side, limit is negative infinity. On the left-hand side, let's say 5. It's fine. But on one side is definitely an asymptote, and this is enough to call this line a vertical asymptote. Okay, that was actually the plan to finish. What you can do, we still have nice section, really short, 2.3, just the basic like properties, basic laws of limits. Please watch it, okay? You will watch the graphs, 1.1, and you can watch 2.3, okay? On that YouTube. I mean, it's just me talking about these functions and about the basic laws of limits. And then next week we will take, everything and go even deeper. Okay, question. All asymptotes are essentials. Yes, the vertical lines, no values like no D and E. That's good. Okay, that means let's finish the session. You will watch the basic graphs and you will watch the basic properties of limits. And and then you will be good. And of course, you can rewatch Tuesdays and Wednesdays session. Much easier. Okay, thank you. And thank you for the really nice participation. I really enjoy when you answering the questions, because then I know that you are involved, engaged. Okay, thank you. Yes, no session tomorrow, unless you want the session. Oh, because normally I plan the session Tuesdays and Wednesdays. Yeah. Do you want the session tomorrow? Because when it's too many sessions, some students they don't like it. That means no, please use that time to watch 2.3, okay, to watch the video and maybe practice with me along with the video. And of course, 1.1, you can check the basic graphs, okay? That will use that time to watch and study. And you still have your GSG session, I think over the weekend, right? Sunday? Please also join the session. It's really helpful. Okay, you have lots of work to do and I will see you next week. Thank you. Thank you. Thank you, Laura. Thank you, everybody.